And share my screen. Sorry. All right. I think in last class we talked about the. Let me let me move this a little bit. This toolbar a little bit. It's a little. All right. We talked about the additive manufacturing's 10 principle, right? We discussed some of the features, unique features of additive manufacturing with some examples shown here. We talked about the complexity, the variety, assembly, no need for assembly for many cases. Also the benefit regarding the preparation, leading, also the skills for the manufacturing, also how compact, how close manufacturing is with the design process. So these are all the benefits. We talk a little bit the waste during the production compared to some of the subtractive manufacturing process for some applications like the one showing here. Basically, we have, if we talk about some parts with large volume of void, it is more in terms of the material consumption, additive is the better choices compared to those subtractive. You have to kind of waste most of the material, but only have very little left for the products. So in that case, additive is a better choice and has a, I would say, substantial advantage compared to the conventional ones. And we talk about the materials. As you can see here, for the multicolor and multi-material printing, that is not supported by a conventional manufacturing. You have to do some multiple process or assemble a different part together to achieve a different color or different material in the same part, right? And also here shows a example of the functional printing. You could directly print the metal conductive wires and embed the part during the printing process, and such that you will have a direct out of 3D printer functionality. That is not possible with the conventional manufacturing process, right? And also we talk about some of the benefit for seamlessly integrated with the digital processing technologies such as the 3D scanning, right? You can 3D scan a real object and convert this digital file to a physical one using 3D printing. And some of the business could be based on such kind of capability, and which is a, I would say, also a revolutionary change compared to many other manufacturing process. All right. So besides those 10 specific principles, I also would like to talk about some of the thoughts on additive manufacturing in terms of the complexity versus cost. So as I mentioned, the complexity for additive manufacturing is almost free. That means print the product with a higher complexity versus a lower complexity. Um, the actual effort and the cost will only rely on how much material consumed. So that is quite different from the traditional manufacturing process. If you look at this graph, here this curve shows the complexity versus cost relationship of a traditional manufacturing process. And as you can see here, with the complexity becomes higher and higher, it turns out you will have a higher and higher cost. So if you talk about some of the injection molding or casting process, that is so true, right? So for example, if you want to produce a much more complex product than what you have currently, probably you want to make a tool, manufacturing tool first. And that tool is quite expensive. And also the complexity of the product will affect the manufacturing process a lot, which requires some special treatment or extra time or other extra cost. So which will make the total cost for the product with complex shape more and more compared to the product with simply a more simple geometry, right? But for, as I mentioned, for additive, so basically it's a straight line, means, well, you have a complex geometry, that's fine. But just the amount of material consumed will matter. No matter how complex the geometry is, just to check how much material it will consume. And printing a simple part versus printing a complex part will make no difference if the material consumption is similar. So that is really I would say, a very important benefit for additive, especially when you think of selecting the material process, the manufacturing process for certain product. You need to keep this in mind. If you have a part with much simpler geometry, you could think of using the traditional one. It makes not that much different. But if you have a very complex part, probably the additive manufacturing is a better choice. And plus, for some parts, like the one showing here and here, it's for the conventional manufacturing process, it's not even possible to produce them, right? You have to, probably you want to, if you produce the one showing here, this very complex shape, probably you need to divide it to different assemblies and assemble them together. No way to print it in a whole part. So these are the things you want to keep in mind, all right? Complexity versus cost. Any questions so far? Okay. Another thing is the units versus cost. That is the production volumes versus the cost of the production. Again, if you are talking about a high volume manufacturing, probably you want to look at the conventional manufacturing. So it tends to have a higher cost if you only have very small amount of production requirement for a product. And again, for the additive, it's almost unchanged. If you, no matter you have a lower production volume versus a higher production volume. Also, you want to note that the cost here we are talking about is the cost per unit. So if you ever learned about the conventional manufacturing, especially, for example, those injection molding or casting, the cost for preparing the tool is substantial if you only produce small amount of parts. That is, if the number of parts you are trying to produce is low, and after distribute the cost to each of the part, this unit cost will be pretty high, right? That's the situation for the conventional manufacturing. But if you scale up the production, the cost per unit will become lower and lower. And that's why for the conventional manufacturing, they are quite suitable for producing zillions of parts with identical, which are identical to each other. So, but for additive, it's again that's a straight line, which is parallel to the to this axis. That means, well, for the unit cost of the part produced using additive, its cost is unchanged. I mean, no matter you are producing a high volume or low volume, this unit cost is the same. So, and also here is a intersection between this curve and this one. So you should be able to understand if if the production volume is go beyond this point, probably adopting conventional manufacturing is a better idea, because past this point, the cost for conventional manufacturing is lower. But if you have any production volume is below this point, well, additive manufacturing in general is a better choice. Actually, in current industry, or those entrepreneurship startup companies, what they do is, in the prototyping stage, they use additive to produce only quite small amount of products for their testing and verification or promotion, right? But when they confirm their design, when they decided to scale up the production, they will go to the conventional manufacturing process. So that's how this kind of innovation or startup company work right now. And that is also another thing you want to keep in mind when you have the question whether you should go conventional manufacturing or additive manufacturing. All right. So any question for this figure? Okay, good. So for additive manufacturing or 3D printing, there are issues. The biggest one, I would say, that is the part accuracy. As you can see here, these two parts are produced using additive. You will see the so-called step case appearance. Because of its layer by layer manufacturing manner, there will be such kind of inaccuracy produced. Also, there will be some shrinkage and distortion due to the process of additive manufacturing. Also, the material can be used in additive manufacturing is quite limited compared to the whole family of engineering materials. Those materials can be used in additive is still quite limited. So that's why a large amount of work in the additive manufacturing innovation is in the material science. So researchers and practitioners in industry are working towards to include more and more materials in additive manufacturing to satisfy different needs. And so if we talk about the most I would say the goal of additive, or the holy grail of additive manufacturing, will be if we could have a layer-based process that can compete with injection molding or metal casting on the basis of speed, cost, and part quality. That will be the ideal case. That will be the ultimate goal for additive manufacturing. I mean, in other words, current additive manufacturing process can hardly be compatible with injection molding or metal casting in terms of speed, cost, and part quality. Although there are some exceptions, meaning in some applications, additive is the the best process compared to any other manufacturing process. But in general, it still cannot compete with those conventional ones, and that is the goal for every researcher and industry people working towards. All right. And as I mentioned, the for the additive manufacturing, the most basic concept is we produce this part by adding layers of material one at a time, and accumulate the layers again and again until you complete the production of the whole part. As you can see here, starting from the CAD model, the first step will be generate the slice, right? Basically, the CAD model, the 3D object will be sliced into layers. And with these layers, the additive manufacturing will start its production by printing these layers one after another, right? That's the basic concept of additive, right? And there are different materials for additive. There are liquids materials. Basically, they are cured layers they are cured layer by layer into the solid polymers, and there are powders. Basically, they are aggregated and bonded again layer by layer. And wires and filaments that is melted and deposited in rasters or vector passes. Also, there are some additive manufacturing process utilizing the solid sheet. So these sheets are laminated to create these solid layers like the one showing here. But no matter what material utilized in the process, still additive manufacturing processes use the layer by layer manner to produce the whole 3D product. So that's the common, I would say, basis of the additive manufacturing process. So I will give you a little intro of different materials in the later slides. But if you have any questions so far, just let me know. Any questions? Nope. Good. So based on the ASTM F-42 categories, there are 7 different categories for additive manufacturing processes: material extrusion, powder bed fusion, vat photopolymerization, material jetting, binder jetting, sheet lamination, and direct energy deposition. These are the big categories, and of course, under each of these big categories, there are different small subcategories. There are variations under each of the categories, and probably we will focus on the material. We will probably introduce the material extrusion, also the vat polymerization, jetting, and some of the direct energy deposition and so on. I would say all these will be briefed, but the focus will be the material extrusion and the vat polymerization. And these are the ones, you will actually operate the machine which are under these categories. And that's why they are the most important ones. And probably that these are the ones you will work with when you get a job or get into research. All right. Let's take a closer look at it. The first process I'm going to talk about is the VAT polymerization. And the representative process is the stereolithography. So this is invented by the Chuck Howe in 1984. So basically, the material utilized is the liquid polymers. And this liquid polymer could be cured by the light energy. For example, the lasers, ultraviolet, or even natural light. And the process for fabricating a solid part out of a photosensitive liquid polymer using a direct laser beam to solidify the polymers. So basically, basically how the material is invented, the people just combine those physical sensitive agent together with some normal polymers. And of course, it requires a lot of trial and error effort. And after all, they figure out some of the combinations of the photosensitive agent together with the polymers, such that they could be successfully cured under the light energy is applied. And the main player for such process is the 3D Systems. Actually, this company is founded by this inventor, Chuck Howe. And that's why they have the advantage compared to some of their competitors. For example, there are some new game players in this domain, like the Formlabs, right? It is a company also producing the SLA machines. And we have the machine in our lab session, and you will have the chance to operate that machine. So in order to let you have some more intuitive understanding of the process, let's look at a video. Are you able to see the video? No? Yes?
No.
No? Okay. Okay, let me
unshare your screen and then reshare it.
Yeah, I think that's it. Let me close my sharing and reshare. Where is it? Yep. All right. Can you see it right now? It's a YouTube video.
Yeah.
Okay, good. All right, I think that's it. And let's go back to the slide. As you can see here, that different variations under this stereolithography process. There's a top-down process as well as the bottom-up. What you have seen in the video is a top-down building process. That is this moving. Let me have a pen here. This moving platform starting from the this top of the tank, and when one layer is cured by this light source, it will move a small amount of distance towards the bottom of the tank, and then another layer is cured, and so on and so forth. Right, that's the top-down process. Another process is the bottom-up. So at the very beginning, this platform is at the bottom of the tank, and the light source is placed at the bottom as well. And after one layer is cured, this platform is moving towards the top, and then another layer will be cured, and so on and so forth. So these are the two different processes. And so I have a question for you guys. Can you think of what could be the benefit to have this bottom up? Apparently, this top-down process is it appears first, and then we have the bottom-up process. So that means there's something beneficial to have this bottom-up. And can you think of some of these? Okay, I see Q raise hand. So you can answer. You can just speak out. Q.
It would just requires less resin because you don't need like the full depth of the tank to be filled with the liquid.
Yeah, exactly. I think you got the idea, and yeah, it is, and also it's already shown in the figure. See, so this have a much depth. I mean, it has a tank with more depth compared to this one. That is because if you want to build the same part, you have to make sure the depth of the tank at least has the same depth as the height of the part, right? That's how you could build it. But in this case, what you need to do is just to make sure the newest layer to be produced is still dipped in the resin in the tank, and that's it. So you don't have to have a really steep tank in this case. You just make sure the material inside this tank is enough for you to build the part. That's it, right? But for this one, you have a lot of excess material in the tank. And that's why people are looking at this bottom-up process. And that's why you have some new process like this. If you see this GIF file, that's how it works, right? So you build one layer, and then there's a motion, there's a mechanism push the material from one side to another, and then you build another layer. So the second question here is why you have this part, why you have this kind of a blade to push the material from in this kind of motion. Why this is necessary? Any question? Any idea?
Maybe to like maintain consistency of the layer thickness?
Well, no, it's not the case. Actually, the layer thickness is controlled by the motion of this lifting mechanism. Any other thoughts? Okay, let me explain it. You just imagine if the light, let me maybe erase this. It's a little messy. All right. So let's say you have your layer is cured here, right? Cured at the bottom, right? So when the layer is cured, when the material is cured, that could be quite sticky because it becomes solid or semi-solid of the layer, and it could be attached to the bottom of the tank. And if that's the case, when you lift your part, that will be a cohesion adhesive force between the part and the bottom of the tank. And it turns out it will prevent this lifting motion, and turns out you will have a damaged part. So that's why you have to have a cutting force to cut the part, to separate the part from the bottom of the tank. And that's why you need this kind of motion to make sure this part will not stick to the bottom of the tank. Understand it? And if you take a look at this this illustration again, actually you will realize, well, the building time for this process actually rely on this lifting and also as well as this separation motion. So you might ask, if there is any way to kind of reduce the building time, because if there's a way to prevent the sticking of the part with this bottom of the tank, then we actually do not need this kind of separation motion. So there are some newly invented process like the one shown here. This is the continuous liquid I don't quite remember the full name, but it's a continuous motion. As you can see here, apparently there's no this separation motion again, and it just has a lifting motion. And as you can see here, it's much faster compared to this process, right? Because you are actually saving the time to separate the part with from the bottom of the tank. So how they achieve it? And I will definitely introduce the details, but let you know what they do is, let me draw it. So let's see, this is the bottom of the tank, all right? And this is the risings in the tank, all right? So they turns out they managed to have the so-called dead zone, or a actual layer of oxygen to prevent the touch of the resin and the bottom of the tank. That means between the liquid resin and the tank, there's always another actual oxygen layer to make sure they are not touch to each other. So in that sense, there's no risk to get the bottom of the tank attached to the part, the newly generated layer cured. So that's how they eliminate this separation motion, and that's why they could have such kind of a much faster process. But that's not easy. I mean, I just give you a very brief description of what they did. And definitely when we talk about the stereolithography, I will give you more detailed introduction there. And also I will discuss some of the still existed problems even for this process. All right, but just let you know, there are some development in this domain to make this faster, higher production rate. All right, any questions so far? No? Okay, good. Then we have the material extrusion process, the so-called fuse deposition modeling. And this fuse deposition modeling actually is copyrighted by its inventor, Scott Crump. And people also call it fused filament fusion, right? Which is another name, does not have copyright. But I just want to, I mean, because this FDM is more popular and is widely used, so I just still use this FDM here. But this is reinvented by Scott Crump in 1980s. Now it becomes open sourced, and probably I don't remember the exact year it becomes open source, but probably around 2012 or 2014. I don't quite remember. But if you look at the amount of new companies who produce 3D printers, you will see a dramatic increase around 2012 or 2014. That is because this process is open sourced, and more and more company get into this area and produce this this kind of a machine. And right now, the fuse deposition modeling machine, I mean, if you talk about some, I would say consumer level, which is, they are quite affordable. For example, the Prusa 3D machine we utilized in our lab only costs like several hundreds dollars, 700 something. There are even cheaper ones you could easily find on Alibaba or Amazon or whatever. So because machine and process is quite simple, and its material is cheap. So that's how it gets more and more popular, and it comes into like schools and even people's home, right? I know some of you have such machine at your home, and definitely it's the most affordable 3D printing process or machines among our other processes. But again, let's look at a video for the illustration. I think, let me stop the sharing again. I think I need to open the video first. Okay, there we go. Yeah, thank you, Luis. Continuous liquid interface printing. Thank you. I remember its acronym CLIP, but I don't remember its full name, but thank you. All right, can you see the video?
Fused.
Can you see the video right now?
Yep.
Okay, good.
Deposition modeling, or FDM, is a layer additive manufacturing process that uses production-grade thermoplastic materials to produce both prototype and end-use parts. This technology is known to accurately produce feature details and has an excellent strength-to-weight ratio. FDM is ideal for concept models, functional prototypes, manufacturing aids, and low-volume end-use parts. The FDM process begins by slicing 3D CAD data into layers. The data is then transferred to a machine, which constructs the part layer by layer upon a build platform. Thin thread-like spools of thermoplastic and support material are used to create each cross-section of the part. Similar to a hot melt glue gun, uncoiled material is slowly extruded through dual heated nozzles. The extrusion nozzles precisely lay down both support and thermoplastic material upon the preceding layers. The extrusion nozzle continues to move in a horizontal XY plane while the build platform moves down, building the part layer by layer. The finished part is removed from the build platform and cleaned of its support material. Raw FDM parts have visible layer lines. However, service providers such as Solid Concepts offer multiple finishing options to create smooth, even surface parts including hand sanding, assembly, and cosmetic paint. Since FDM parts are constructed with production-grade thermoplastics, including ABS, polycarbonate, and Ultem, they are both functional and durable. FDM is utilized in a number of industries, including aerospace, automotive, industrial, commercial, and medical.
All right. Okay, let me go back to share the my presentation. Just 1 second. I think there is. Okay. As you can see here, there's a major company, which is the Stratasys. Also, it is based on this, I would say this is a founder, also the inventor of this process. And this Stratasys play a very important role, especially in the early age of fused deposition modeling market. But now more and more small and medium size company getting into this area to deliver cheap and I would say very good quality machines to the consumers as well as the some of the researchers as well. But you will play with this kind of printers quite a lot during the lab sessions as well as the project. If you do the project, probably you want to fabricate the majority of the part using this process. All right. So another one is the powder bed fusion. So there are also different variations: selective laser sintering, direct metal laser sintering, and so on and so forth. So in this process, the thermoplastic powders are utilized. Also, there could be some machines utilizing metal powders, right? And then you will have a laser beam selectively scan the powder bed. So it will draw a pattern on the powder bed and fuse the powder only where the laser scans. And then this platform will go towards the bottom. I mean, go downwards, and there will be a leveling roller to spread another layer of material onto the newly built layer, and another round of laser scanning will be there to fuse the new added powders. And this process will be continuously repeated until the whole part is built. Okay, there are multiple companies like 3D Systems and EOS. They produce the high-grade machines utilizing this powder bed fusion, especially the EOS, which is, if my memory is correct, it's a German company. It is the big player in the industry in the metal printing, utilizing the powder bed fusion. Again, another videos. I think stop sharing.
Selective laser sintering, or SLS, is a rapid prototyping technology that turns 3D CAD data into physical parts in a matter of hours. SLS is an additive manufacturing technology that uses powdered nylon 11, nylon 12, and PEEK materials. Parts produced are lightweight, highly durable, and both heat and chemical resistant, making SLS an excellent choice for producing production parts without the expense of tooling. The SLS process begins by splitting 3D CAD data into thin cross-sections or layers. The data is then transferred to the SLS additive manufacturing equipment. The machine then begins to create the first layer. After a leveling roller spreads a thin layer of powdered material across the powder bed, a CO2 laser traces the cross-section on the material. As the laser scans the surface, material is heated and fused together. Once a single layer is complete, the powder bed is lowered to make room for the next layer. More material is introduced from the powder cartridge and rolled out smooth, while unused material is recycled. The process is repeated, building layer upon layer until the part is complete. As SLS parts are built, they are encompassed by unsintered powder, which provides supplemental strength and eliminates the need for support structures. Complex designs and assemblies, once thought impossible, are now being redesigned with SLS as cost-effective integrated structures. Solid Concepts manufactures parts utilizing nylon with property-enhancing fillers to create rugged SLS parts suitable for a variety of prototype and production applications. Typical uses for SLS include tools and fixtures, fuel tanks, flight-rated components for unmanned aerial vehicles, automotive designs, air ducts, architectural models, and artistic sculptures.
Okay. As you can see here, the leveling roller plays an important role in the process, right? So so it's also a left to right motion, similar to stereolithography, but the purpose for this motion is totally different. For the stereolithography, I mean the bottom-up process, this motion is used to separate part from the bottom of the tank. But in this case, this motion is for spreading more material onto the newly generated layer, right? Just to be aware of the difference, although they have similar motion, right? So another process is the material jetting. So this material jetting is quite similar to what we have for the ink jetting machine for printing the documents. So the ink will be deposited onto the platform for one layer, and then the platform will move towards the bottom. Move down, will be lower, and another layer will be printed onto the previous layer, and this process will be repeated again and again until the whole part is built. So there are quite different material could be used, like the photo polymers, thermoplastics, or even metals. So actually, we have such a metal jetting machine in our Brinkmann lab. It is invented by Vader Systems, and the Vader system was acquired by Xerox in 2019, and now this technology belongs to Xerox right now. So it's similar. I mean, although the different material are utilized, but they all share the common concept for the production. And so let me play the video again. Okay, I think that's it. As you can see, the benefit for this process is similar to the 2D jetting, right? The 2D printer for printing document. It's quite easy to print multiple materials. As long as you have different jetting head, the printing head, you could easily print different colors, different material through the different printing head. As you can see here, you have the part produced using material jetting could have a really nice features and colors and multiple material and so on and so forth. And here shows a example that is produced using the Veda machine, which you can see the aluminum material is jetted through the printing head. It turns out you have some really complex shape like this. And I think we can have a break for 10 minutes. Let's go back at 11:17. All right. Okay, let's come back. So another process is the binder jetting process. Also, it's quite similar to the 2D inkjet printing, and it will spread a layer of powder. Then the printing head will inject the binder to glue those powder together. And after the printing is completed, those loose powder will be removed surrounding the part. And another post-processing is necessary to provide the necessary strength and to debinding those glues. So if you look at this illustration figure, it's a breakdown. It's a breakdown of this binder jetting, and first of all, a powder will be applied, and then the binder will be added there, and then the platform is lowered. Another layer of powder will be applied again, and also the binder will be added as well. So this will be repeated until the whole part is produced. Turns out you will have this geometry, but that's not the final part. You have to, if you have to have a post-processing to have a better, to have the part with better strength. So once you take out the part from the excess powder, basically you are getting a grain part. If you ever learn about the those casting process, you should be understand the so-called grain part has the geometry of the product, but the mechanical property is not that good. In other words, the strength is low, so it requires a debindering process to remove the binder and solidify the part and improve the strength of the part. So basically, in this binder jetting, it required the exact same steps as what I mentioned. Also, for this binder jetting versus this material jetting, can you tell some of the detail? I mean, can you tell some? Can you tell the difference between the two? Any idea? No. Okay. So for this one, for the material jetting, so all the material for building the part is coming from this printing head, right? And there's no binder utilized. So the material will be jetted from this printing head onto the platform and add upon one existing layer and repeat it again and again. But in this case, for the binder jetting, there is powder utilized. And also the material jetted from the printing head will be this binder or glue to glue the powder together. And also this will be repeated again and again before the part is completed. And also you need a post-processing to solidify the part and remove the binder. So that's the major difference between this binder jetting and material jetting. All right, clear? Are you guys clear about it? Any questions? Okay. Nope. Okay, good. But again, let's look at a video about this process. Just 1 second. All right.
Binder jetting additive manufacturing is a process inspired by the technology of inkjet printers. In this process, a liquid binder is selectively deposited on a powder bed with a print head. It is a growing process that allows the production of parts for the manufacturing, medical, and dental industries. This technique enables the production of metallic and ceramic parts, as well as sand molds for castings. To start the process, a 3D drawing is imported into the printer software. The powder to be used is placed in a dispenser, which ensures a constant supply during printing. First, a powder layer of a specific thickness is spread. Thereafter, the printing head, moving on 2 axes, projects the binder where necessary. Before moving on to the next layer, the solvent contained in the binder is evaporated by an incandescent lamp. The powder bed is then lowered and a new powder layer is deposited. Therefore, the production takes place in a series of steps that build the part layer by layer. When the cycle is completed, the binder is cured by placing the container in a furnace. The temperature and time depend on the type of binder employed during printing. After this step, unbound particles are removed to reveal the part or the mold. After this step, the sand molds are ready to be used in foundries. The metal and ceramic parts must undergo sintering, infiltration, heat treatment, or hot isostatic pressing before being used.
All right, as you can see, the post-processing shown there, right? And that is usually a heat treatment to make the part higher strength and remove the binding and removing the binder. And I will go to more details when we talk about this process. And I think you've already visited the Amprint Center, and also we have the Brinkman Lab located with several other 3D printing facilities, machines there. And that's the basis for us, the researchers at RIT, to conduct the cutting edge research in this field. Okay, let's continue and talk about the fused deposition modeling. The fused deposition modeling is obviously the most important process for the material extrusion. And basically, this process utilizes softened or melted thermoplastic polymers, and the material comes through a nozzle, and the nozzle move over a predefined path, and then it will print a continuous trace of the material for one layer. And afterwards, this printing head will move upward and ready for the next layers of printing. So it's quite similar to making a cake, right? Ice cream cake. And here shows how it works in an illustration figure. I think we have watched the videos, so you guys should be familiar with it fair enough. And this is again a video, and I would like to skip this because it's pretty much the same as what we watched in the last lectures. Then we take a more detailed look at the components of the printers. So first of all, most of the machines utilize the thermoplastic filaments. And basically it comes in spools or of material wires. Usually it has a dimension 1.75 millimeter or 3 millimeter as the diameter. For the nozzle, usually it has 0.4 to 0.8 millimeters, and it changes in multiple of 0.1 millimeters. And here shows a illustration. So basically, the filament will go through this feed tube, and then there's a heat sink, which will be heated, and the plastic filament will be melted and pushed through this nozzle. And here the heater cartridge will be utilized to heat the filament, and this heat block will conduct the heat generated by this cartridge. Also, there are a thermistor or thermocouple located here to control the temperature. So the function of this heat sink will be to kind of conduct the excess heat from this transisted from this heat block. Basically, you don't want to overheat the filament in this area, because if the plastic is heated, it becomes softer, and that will introduce the difficulty when you drive this filament to go forward into this part. So definitely you want at this part is still cool. I mean, the filament is still cool. So that's why you want a heat sink to kind of get rid of the excess heat. Usually there is a fan near this heat sink, also for removing the excess heat in this area. So that's how it works for a typical fuse deposition modeling machine. So this is so-called the hot end, right? So any questions so far for this hot end? Okay, good. Okay, let's move on. And usually for many high-grade FDM machine, it comes with a build chamber. So this build chamber will cover the building platform, the hot end, and other components. So why we need this build chamber? The main reason for having this is there is a tendency of the part to be built using fuse deposition model. That is, it will curl up at the corners. And with this building chamber, it maintains a relatively high temperature throughout the whole process, and that will reduce the tendency of part to curl. So if we look at this illustration, I will explain in more detail about the curl happens here. So let's see, you have one layer printed here, and at first it's a hot layer, right? And when you print it on the platform, it will become cooler and cooler, and during this cooling process, this layer will shrink, right? Shrink towards its geometric center in this direction. If you see these two arrows, right? Okay, that is the one layer, and then you will have another hot layer printed onto this cold layer, And because of the temperature of this hot layer and cold layer are different, that means when this newly introduced hot layer becomes cooler and cooler, it shrinks as well, but in a different rate compared to this hot layer. So that will introduce some problems for the curving. And because of the shrinking for both of the layer are similar towards the geometric center of the layer, so it will turns out these two layers will tend to shrink to towards the center, but in different magnitude, because the temperature of the two are different. And it turns out you will have such kind of curling happens during this cooling process when the printing goes on. So that's why this kind of curving happens, and that's why we need a build chamfer. In that case, when we have a chamfer there, and it will keep on heating up both of the layers, both of the cold layer and the hot layer, and make the temperature difference between the two are minimized. And by minimizing the temperature difference and the temperature drop, turns out it minimizes this curving. And that's why we have this build chamfer introduced in many of these processes, fuse deposition processes. But the machine we utilize in our lab does not have this build chambers. So in that sense, you don't want to print a large part with a large diameter, large cross-section area. But the machine is the size of the machine itself limits the part to be printed. So that's usually not an issue for printing it. And another thing is you could apply glue onto the building platform to somehow cancel out this curving, because this adhesive force could pull the part and make it stick to the bottom of the platform. But that's by nature, the problems for this heat treatment based, heat process based fuse deposition modeling machines. All right, any question about this part? Okay, good. Okay, let's move on. So you also want to take a look at the different material properties for different materials could be utilized in the fuse deposition modeling. And besides its fundamental material properties, there are also some features related to how easy this material could be printed using this process, and what will be the temperature set it when you set up your 3D printer. So for the first one, you want to check the printability, and the second one, you want to check this extruder temperature. And I would say to me, the easiest one to be printed is the PLA material. And as you can see, it has the highest score. And the APS is pretty easy to print as well. But there are some new material which are quite flexible, like this flexible material shown here, and for such kind of material, it's quite difficult to print, and it's a little tricky to print. And I will discuss why it is in such case for the flexible materials. Actually, that is because the mechanism for filament fading. So here, where's my mouse? Yep. So this is the fading mechanisms. As you can see here, the filament will go through in this way, and these two will rotate in this direction and this direction. And I think it's a wrong direction. Sorry about that. I think it's in the opposite way. Actually, this one moves this way, and this wheel moves in this way. And basically, with such kind of motion, this filament will be pulled and pushed through this tube towards the hot end. And so there could be some difficulties when you utilize the flexible material. As if you look at the illustration of this feeding mechanisms, so this two will drive the filament into this small hole, and it goes to the hot end, right? That's the typical case. But just imagine if you have a very flexible material or a stretchy material. If there's anything wrong, you could have such problems. Turns out that is really difficult to pull a very stretchy or flexible material to be precisely into this tube. And that's why there's some design minimize the distance between these two driving wheel and this tube. So if you have a design like this, that means this distance is minimized, and that makes the this filament goes into this tube much more easier. And so, but not every machine could handle this kind of flexible material well. It also depends on what kind of feeding mechanism it has. So there are two types. One is the so-called direct drive. So for the direct drive, this filament feeding area is combined with the hot end, right? That's the direct drive. Also, there's a so-called Bowden filament feeding. So here, that's the filament feeding mechanism. And here is the hot end. So these two parts are separated. So the benefit to have this separated hot end and filament feeding is, first, you make this you make this hot end, you make this part a lightweight because you're removing this filament driving from the hot end, right? And the benefit is, if this is a lightweight, when you control the motion of this, because this will move in the XY plane and as well as in the Z direction. If let me draw a coordinate system. Let's see, this is X, and this is Y, and this is Z. All right. So that means for the same layer, this printing head will move in the XY plane, and once the one layer is completed, it will be lifted in the Z direction, right? So a lighter weight will usually lead a more precise control in the XY and also Z. So that's the benefit for separating this filament feeding part and also the hot end. But the difficulty is, well, you're actually maximizing the distance between this driving versus this entrance of the filament towards the hot end. And the problems described here will be even more serious, right? So usually this kind of printer cannot handle those flexible material well. And in contrast, this kind of direct drive based printer can handle it much better. So that's the pro and the cons for the two different filament feeding mechanisms. And what we had at our lab, I mean, the Prusa 3D machine, it has the direct drive. So it is possible to print some flexible material. And so according to the needs for your project, I will think of purchasing some flexible material for you guys. Because I mean, in the last year's project, I asked students to design a car. Some students were thinking about printing the tires using our printer, or some of the flexible part using our printer. So I purchased a little bit, but it turns out they didn't have the chance to actually print the part. But in this year's class, although we haven't decided what project go with you guys, but that's possible for you to think of some flexible part. All right. So any questions for this filament feeding mechanism? All right. Another important aspect is this toolpath strategies. As you might know, for printing a part using fused deposition modeling, the interior region of a layer actually is not 100% dense. Usually it has this sparse patterns. So, and these patterns will sometimes produce different material properties. But it turns out, even you choose different patterns for this infill, the part strengths are quite similar to each other with different infill patterns. That is because we figure out the most of the rigidity or strength is contributed by the strength of skin. That is the profile of the one layer. And so that will make things simpler. That means you don't need to worry about too much about these kind of infill patterns. You just choose some of them, and that's it. Probably you want to think about the strength weight ratio. That's the only thing you want to take into account when you choose the infill percentage. Here shows the percentage here, right? That's 20%, 40%, 60, or 80% of the material. And this axis shows different patterns. And these are the parameters you could play with when you work with the Prusa 3D printers. But again, it doesn't make too much change, even you choose different percentage and different patterns. All right. And usually the simple linear rastering is the most chosen one for the feeding patterns. Also here shows you some of the high-grade commercial machines produced by Stratasys, and you can take a look at it if you want. But there is one question I want to ask you. For this kind of fused deposition modeling machine, not only the one from Stratasys, but more in general, right? Is the accuracy for XY plane and Z direction the same or not? Anyone want to answer? Any idea?
Dr. Shang, could you repeat the question again, please?
Yep. Is accuracy for XY plane and Z direction the same for the part printed using the fused deposition modeling process? Any idea? Who can
I
give
will
me an
say
answer?
yes, but
Uh-huh.
I'm not sure.
You say yes or what? Or no?
Yes. Yeah, I will say yes.
Okay. Any other different opinions or not?
I say no.
No? Okay. Well, we have yes and no, and the answer is no. Because of the if you take a look at the process, right? We have more continuous motion in XY plane, but a discrete motion in the Z direction. And also because of the layer by layer processing pattern, and turns out there will be a weakness along the Z direction as well as the part accuracy. So it has a higher accuracy in the XY plane versus the one in the Z direction. And I will talk more about it in the later slides, but just let you know that it has a lower accuracy in the Z compared to the ones in the XY plane. All right. Also, if you want to use a Stratasys consumer level machines, you want to check its menus for the different materials and the different conditions for printing parts using different materials. But I will skip the details here. So if you ever look at their menu, the description for the accuracy are usually like this. So the parts can produced within an accuracy of positive negative 0.127 millimeter or positive negative 0.0015 millimeter per millimeter, whichever is greater. So this basically you want to compare this and find the one which is greater as the accuracy. All right, that means it can only produce a feature as large as, as smaller as the number which are the greater one among the two. Why there are two number here? That is because when you print more, in principle, when the part is larger, the accuracy or the error, printing error will become larger because the plastic expansion or the shrinking during the printing process. That is similar to some other process for the plastic, like the injection molding. But let's look at an example, specific example, and see how we could utilize the two to decide which will be the accuracy. Let's see you have a part with a 100 millimeter length. So what will be the tolerance range for the dimension printed with the machine? So what we want to do is we want to compute its error utilizing this one, because the length of the part is 100 millimeter. And for 1 millimeter, you probably will have 0.0015 millimeter error. And it turns out for 100 millimeter, the error is this amount, 0.15 millimeter. And compare with this one, right? Compare with this one, it turns out you will have the ultimate accuracy because this this 0.15 is greater than 0.127. So in that case, the error of the plastic expansion or shrinkage dominates the error, and the accuracy should be this number. And also another resource for the error come from is the size of nozzle. So because the size of a nozzle is fixed for a specific nozzle, in that case, it is a fixed number. That's why we have this 0.127 millimeter here. So if we print a feature or part which is smaller, which is quite small, like the one shown here, 10 millimeter, and let's compare which error dominate. So again, we compare this dimension related error, and it turns out it's pretty small. It's 0.015 millimeter, which is smaller than this absolute error, 0.127 millimeter. So we chose this one as the overall error because due to the hardware, the dimension of the nozzle, the size of a nozzle, even you only have this kind of error by this computation, it cannot be achieved, right? So that's why the error is this, and this will be the dominant factor for the error. Do you guys clear about it? Are we clear
I have
about
one
it?
question.
Yeah.
The millimeter by millimeter dimension, what does that mean?
That you mean this one, right?
Yeah.
You mean this millimeter over millimeter, right?
Yeah.
Okay, that means if you have 1 millimeter, if the part size or feature size is 1 millimeter, then the error is this, is 0.0015 millimeter. Because for the plastic part, thermoplastic part, you always have the thermal expansion and shrinkage before and after, during the process. And that will introduce the error. And that error is dependent on the dimension of the part. So that's why we have error like this. In principle, the larger the part is, the error will become larger. You get it?
Yeah, thank you.
Yep. And this one, as I mentioned, this one is this number, this absolute number actually is actually from the size, the dimension of the nozzle. So that also introduced the error as well. Why? If we look at this figure, that's the cross section of the trace printed. Let me, where's my mouse? Okay. So this is the printed trace on the plane, right? If we look at it in the side view, in this direction, then you will only have this kind of circular cross sections. For example, you want to print a 0.6 millimeter trace. You could either use two such kind of trace to represent this 0.6, and then you have an error 0.2, or you just use one trace to approximate this 0.6 millimeter, and turns out you have negative 0.2 millimeter. So that's why you have such kind of error, because you can only extrude a trace in such a dimension because of this nozzle size, nozzle dimension. And this kind of error cannot be avoided. And that's the resource for this error. So now you get it? Any question regarding this part? Okay, good. So just keep in mind, the error of FDM comes from the two aspects: printing head size or nozzle size and material shrinkage. And you need to use the two numbers to compute your accuracy or error when you have a specific question. And that will make difference. All right. So another part is about the post-processing. For the printed part, as you can see here, this is the one you take out from the 3D printer. But you can see the surface is not accuracy, and you have a lot of roughness there. There are multiple ways to improve the surface smoothness. For example, you can sand it or paint it, or some of the chemical treatment. For example, for the ABS material, you can easily use some solvent vapor, and basically you just put it into a chamber with the solvent vapor there, and you make it stay inside the chamber a few minutes, and take it out, and you will have this kind of nice smooth surface. So another very simple way to post-process your part is to paint it, right? You can always paint it using different paints. So after I discussed the basic concepts of fused deposition modeling, I would like to introduce some of the new development. I think the time is almost up, so maybe we stop here, and in next class, let's talk about some of the new development, new variations for the fused deposition modeling. And I think after this lecture, you should be able to, you should be able to have the background knowledge of the fused deposition modeling machine, and that will help you to operate the machine in the lab session. Okay, any questions so far?
Nope.
Nope. Okay, good. I think it's a little intensive lecture for today's lecture compared to the one previous week. But I think it's the concept of this process, fused deposition modeling, is simple, so shouldn't make too much difficulty for you guys. But I welcome all your questions, and just shoot me an email if you want to talk with me separately. Also, if you have any problems with your labs, just make sure to let the TAs and myself know, and we will help you. All right. Okay, if you have no more questions, that's all for today's lecture, and look forward to see you next week or before.
Thank you, Professor.
Mhm.
Catch you later.
Thank you, Torshai.
Yeah.
Have a good day.
Yeah, you too. Thank you, Chris and Angela.